Welcome to the another video of electric drive. So here our objective is to determine the equivalent drive parameters. The equivalent drive parameters mean what? Means a drive is setup is right is having a motor with a load and other to find out the J equivalent and what is the total torque, equivalent torque and equivalent inertia, that is the drive parameters or in case. So if I know the what is the inertia and the torque and I can get what is, if I know also the omega m and J and T, we can put or we can get what is the electromagnetic torque required for that particular drive. So determine the equivalent drive parameter for this one is for translational motion. Translational motion, translation load. So how does it look like if I do the diagram? Let us say you have got a motor. Now this motor is attached with, it can be attached with a coupling. Now here it is attached with another load, or it may be a drum. Maybe this is a load or it may be a drum, and you have got the wires wound over here, rope or some mechanism over. So and here you have got a mass or load. So now if your objective is obviously to lift this up, if to lift this up you will say, let us say the having it with a velocity v. So V is positive. Here the weight of the mass is m. Obviously because of gravity m and g, that is a force which is pulling it downward. And you need to give a pull over here. So you need to rotate it like this anti-clockwise. To rotate it anti-clockwise, you will also try to rotate this side also anti-clockwise. Anyway, you have to give a electromagnetic torque in the same direction of that motor motion. So omega m, if it is the direction of the motion is taken positive like this, so Tm is positive. Load torque will obviously will be in the opposite to the electromagnetic torque, and load torque will be like this. So here the load torque is the force, and because of the gravity, this is the force which is acting downward. So if there is a motion like this, in that particular case, how you will write? So how to determine that if the force on the load is F, then how much is that effective torque? What is the effective torque that look at on the motor end? So here there is no gear, it is directly connected to the drum, but usually it is connected with a gear and then connected with a drum. So just we added over here the gear, and that gear may be given as a turn ratio, which is N1 by N2. So obviously the rotor speed of the drum is very low, so the number of teeth on the secondary will be high, and this value will be lesser than 1. A value will be less than 1. And the inertia of the motor is J0 because the motor is having its own weight, and there can be inertia of this drum or this winch, and there is also the inertia of that mass is m. So now to find out what is the equivalent inertia referred J equivalent, we can use the kinetic energy and we can have this fictitious J equivalent, half J equivalent into this J equivalent is also running at a speed of this omega m. So omega m square will be equals to half J0 omega m square plus this. After the gear there is this drum is there, so we can write that this is half JW. The speed over here will not be same as omega m. This speed will be definitely different. So let us write down this speed as W. Let us say this is JL and omega L. JL stands for the inertia load of the inertia load, and omega L is the radian per second, that is also rotation of this load. So instead of W, let us write this as L and omega L square. Correct? Another is here you have a linear motion which is moving upward. So I have got another is half m, with the velocity is moving, it is half mv square. If I equate the kinetic energy, it look like this. Correct? Now this velocity part what we have and this rotation part is omega L. So what I can write is that this omega L and the velocity part, right? This, from these two things we can get some conclusion out of it, that this velocity must be equal to omega L times of the radius of the drum, right? If this is the radius of the drum, so this is like this. So instead of V, we can write omega L into R. That also is possible, right? So let me write down, instead of V, we can write down here as omega L into R whole square. Now from here we can write the J equivalent is equal to J0 plus JL. Omega m cancel. Here it is omega L, so omega L by omega m whole square plus m. Here also we have omega L square R square by omega m square. So like this also we can write, or else we can write V square by omega m square. Now this ratio is nothing but A, so we can write this as J0 plus JL A square m, this is A square into R square, like that. We can write like this, and that's how we can write this equivalent inertia in case of translational load. That is, if linear load is there, if linear motion is there, like linear motion is not rotational motion, another is a straight with a velocity v, translation motion is there. In that particular case, we have to use this formula. If the force is given, mass is not given, so instead of mass we can also write this as force by gravity, G. Like that also we can write. Now if we equate the power at total power, so we can write that let us say the equivalent torque is TL equivalent, that is equivalent torque that is reflected on the motor side with the multiplication of omega m is equal to TL0, or TL0 is what? The load torque TL0 of the motor. Another is another load is because of this mass, and this is having inertia, though it can have a load also. Let us say this is TL1. So we have got a load torque TL1. We have a mass M and G. This is the force, another load over here F. So TL1 and F, right? And TLL0 is because of its own weight. There is another load torque TL0. So we can write here we have TL0 multiply with omega M. TL1, usually TL0 is very less. DL1 into omega L plus, because of the weight there is a force. So how this force and torque is rated? Okay, let us say the power is there. Power is force into velocity. Now it's okay, good. Another thing is that if this gear is not 100% efficient, or there is some slippage over here, slip means it is not a perfect grip is there. So there may be chance that efficiency is not 100%. So the efficiency factor will come into picture for this load, translation load. And it will also come into effect for this rotational load, because efficiency factor will be there after the gearbox. So it will be there for both of them, but it will not be there for the motor, right? So we can write down in one line TL equivalent is equal to omega M, and this cancel and it will come here, and lower bottom TL0 plus TL1 by eta. Omega L by omega M is A plus F by eta. V can be written as omega L into R divided by this omega M, correct? And now this can be written as TL equivalent is equal to TL0 plus TL1 by eta into A plus F by eta into A times of R, like this. So we can get what is the equivalent torque referred to the motor end, and also we have find what is the equivalent inertia referred to the motor end. So knowing these two, equivalent torque, equivalent inertia and omega M, we got the entire setup. We can write a dynamic equation for this drive. Okay, so in the coming videos we will see some numericals based on this. Thank you.